Hi everyone. It's my great pleasure to introduce Laura Minet. Laura is currently a postdoc and she's splitting her time in earth sciences with Professor Diamond and in civil and mineral engineering. So she did her PhD in civil engineering, working on air quality modeling at different scales and neighborhoods, city, regional, the level of regions. And she's been very interested in the interactions between transportation scenarios, transportation policies, and air quality health outcomes. So recently she's been, among many other things she's doing, she's been leading a large collaborative project in Quebec with the Ministry of Environment and Climate Change in Quebec, Environment Canada, and the University of Montreal, looking at very long-range scenarios for transportation policies, transportation technologies, climate change, and their impact on air quality. So I'll leave it to you, Laura.
Thank you, Marianne, for the nice introduction, and thank you for having me here today. So today in this seminar, I'll mainly present you the research that I have led during my PhD at U of T, and this focused, as Marianne was saying, on finding solutions to minimizing population exposure to air pollution. So briefly, as you're probably all aware of, ambient air pollution is a serious threat for human health. The health risks associated with air pollution include acute effects such as stroke, hypertension, and long-term effects such as cancer, diabetes, or cardiovascular disease. In Canada, there are 14,600 premature death yearly that can be attributed to exposure to ambient air pollution, which corresponds to $114 billion of health expenses. And in the GTHA, there's a report of medical officers in health that have estimated in 2014 that 700 premature deaths could be attributed yearly to ambient air pollution. So as a consequence, it's essential to minimize population exposure to air pollution to tackle this threat to human health. In Canada, the on-road transportation sector represents 22% and 18% of the emissions of nitrogen oxides and black carbon. Both nitrogen oxides, NOx, and black carbon, BC, are considered as a marker of traffic-related air pollution, and in cities, the proportion of the NOx and BC emissions from the on-road transportation sector is even greater than 20%, which means that it's essential to design transportation systems that limit the emissions of air pollutants. To reduce air pollution, we need to understand the factors impacting air quality, and they can actually be divided into four main categories. So first, the emissions of air pollutants obviously play an important role in air quality. We've seen before that traffic represents a large proportion of the emissions of air pollutants in cities, and there's a high correlation between traffic emissions and air quality. But there's the nature of the air pollutants present in the air that impact the chemical reactions occurring and that modify the air pollutant concentrations. So for instance, some particles get created through nucleation events. There's also coagulation that happens and that forms larger particles. Third, the meteorology can affect the dispersion and the chemical reactions of air pollutants. Wind is going to disperse air pollutants. Temperature and relative humidity can have an impact on the coagulation of particles. The solar radiation also plays an important role on the formation of new pollutants, such as ozone. And finally, the urban design will affect the dispersion of air pollutants. High buildings can trap air pollution in between them, which we call the urban canyon effect. But large open areas will enable a dispersion of the pollutants. And most importantly, the location of residential areas, infrastructures such as schools and offices is going to have an important impact on the overall population exposure to air pollution. So as a result of this, quantifying air pollutant emissions is not sufficient for understanding population exposure. If we tackle the emissions of some specific pollutants at a specific location, this will not necessarily have a direct impact on air quality at the given locations. Among the four influential factors identified here, we really have a direct control only on emissions and urban design, and so my research focuses on those two aspects. So here, in this context, my research is articulated around two main axes, which are emissions and urban design. How can we minimize population exposure to air pollution by altering our emissions of air and by modifying our urban design? So concerning emissions, the questions my research aims to answer can be summarized as how can we reduce air pollutant emissions? What are the benefits of tackling air pollution? And how do emission reductions impact population exposure? Regarding the urban design, my main focus is on how can we best design cities to minimize population exposure. First, I'll begin by discussing my research about emissions and air quality. I've been particularly interested in studying how we can shape our transportation policies to improve air quality and reduce population exposure to air pollution. And I've mainly worked over the past few years on two case studies. So first, I was interested in quantifying the burden of on-road vehicles on air quality and on population exposure and health. And after this, I also wanted to analyze how putting cleaner vehicles on the roads could help improve urban air quality and population exposure and health. So these two case studies begin by analyzing the emissions from the main sources of traffic-related air pollution. But it's not sufficient because the relationship between decreases in emissions and improvements in air quality is not linear. So to respond to these two questions, I've set up a comprehensive framework. And so this framework was set up around a chemical transport model, which is a complex model that simulates not only the dispersion of air pollutants, but also their chemical reactions. It's a very comprehensive and complex model, and it requires information on first all types of air pollutant emissions, whether they're natural or anthropogenic, to be able to model the complex chemical reactions occurring in the air. And it also requires information on land use and meteorology to model how pollutants disperse and react between each other. The output of a chemical transport model are air pollutant concentrations at a fine spatial resolution. And in our case, the spatial resolution we worked with was 1 by 1 kilometer. The emission inventory is very important for this type of model, and so having the most refined inventory possible is essential. So in this framework, we needed to take into account all possible sources of air pollutant emissions, anthropogenic sources such as power plants, traffic, industries, and other sources such as agriculture and shipping. But we also needed to take into account natural sources such as the vegetation, because trees emit a large amount of organic species in the air, and those play an important role in the formation of new pollutants. So it's ideal to have the best temporal resolution of emissions as well, because depending on the time of the day, the emissions can vary, such as the emissions from traffic, which are going to be different in the morning, midday, and afternoon. And the emissions from the vegetation also change because they're very correlated with the sun. Since traffic is the largest source of emissions in cities, it's important to have a traffic emission inventory as detailed as possible. So we've used the results of a traffic assignment model based on travel survey data, which provided information on traffic volume and speed along the different roads of the city. And we've combined this information with emission factors provided by an emission modeling software developed by US EPA and called MOVES, to get an emission inventory for private household vehicles, transit buses, and commercial vehicles. Then, to evaluate the impact of changes of air pollutant concentrations on human health, we've assessed the health outcomes associated with changes in air quality in terms of numbers of years of life lost and number of premature deaths. And so for this, we've used concentration response functions from the literature, and those concentration response functions relate a change in air pollutant exposure with a change in risk of mortality. So here, for instance, for PM2.5, a risk ratio, the RR, of 1.1 for 10 micrograms per cubic meter increase in PM2.5 exposure means that for each increment of 10 micrograms per cubic meter in PM2.5 exposures, there's a 10% increased chance of mortality. And finally, This assessment of health outcomes was supplemented with a basic economic valuation of the social benefits associated with these numbers of premature death. And so for this, we used a value of statistical life, or VSL, which represents how much people are willing to pay to reduce the risk of death. This VSL does not capture the value of reduced, well, it does not include healthcare costs. It only captures the value of reduced risk of premature death. And so the economic valuation we're doing here is expected to underestimate the actual social benefits associated with improvements in air quality. And the study area considered was the GTHA, which you're probably most of you familiar with. There are 6 regional municipalities, and it houses about 7 million inhabitants. So first, we developed a traffic emission inventory for cars and SUVs, trucks, and public transit buses. So trucks, which are represented here in yellow, are responsible for more than half of the traffic-related NOx emissions in the GTHA, and cars and SUVs, which are in orange, are also responsible for a large amount of NOx emissions. But it's the trucks that are the largest emitters of traffic-related PM2.5 and black carbon, and they represent more than 70% of these emissions. However, is cars and SUVs that are responsible for the largest portion of greenhouse gas emissions. In general, the public transit buses, which are here in green, represent a small portion of the total traffic emissions, but they're important because they operate in densely populated areas. So with this framework, the first question I explored concerned the health burdens of the different vehicle categories. How can we guide policies to target the vehicles that have the most impact on health? So to answer this question, I've designed different study cases. So first, I had a base case with the emissions from 3 vehicle categories: private passenger vehicles, commercial vehicles, and transit buses. And then I removed the emissions from each vehicle category separately to quantify the direct impact of these vehicles on the air quality. The air quality model was run for the 3 different study cases, and the output concentrations were compared with the base case. And here this map shows the years of life lost per 100,000 inhabitants attributed to each vehicle category. On the maps, the red color displayed the location with the highest number of years of life lost per capita. We see that the population losing the most years of life due to private passenger vehicles and commercial vehicles is located mainly along the highways and around the airport. The region of Peel, which is known to have substantial truck traffic, is clearly affected by trucks, especially around the airport, which draws in a lot of commercial vehicles. The spatial distribution is different for transit buses because they mainly drive in the city of Toronto, and so the population the most affected by emissions from buses lives in Toronto. I've also indicated here the total number of premature deaths induced by the emissions of each vehicle category. We see that the vehicles, all vehicles are responsible for a large number of premature deaths, but the trucks are inducing the highest number. From the previous results, we can calculate that the emissions from one car or SUV generates $10,500 of social costs in its life, while one truck generates $182,000 of social costs in its life. But why is it important to calculate social costs? It has 2 main implications. First, it's an opportunity to elucidate the external costs of transport services. The economic valuations, they too often neglect external costs, and so this modeling work provides a method to assess them. And then it's also an opportunity to conduct sustainable analysis and compare the social, economic, and environmental costs and benefits of services such as moving around by car or transporting goods in a region. And this leads us to the second study case I worked on. Renewing the fleets of vehicles is a way of reducing emissions of greenhouse gas and air pollutants, since more recent vehicles are usually more efficient. And so I've explored the health benefits associated with a renewal of the different fleets of on-road vehicles. So to study the impact of having cleaner vehicle fleets on population exposure and health, I first considered the base case with private cars and SUVs, public transit buses, and commercial vehicles. And then I've designed 3 main scenarios. So the first one is 100% electric vehicles. So all private cars and SUVs are electric. The deployment of electric cars and SUVs is often seen as the best opportunity to reduce greenhouse gas emissions because cars are responsible for the largest amount of traffic-related greenhouse gas emissions. The second scenario is 100% electric buses. So all transit buses are electric. Even though buses are not responsible for large greenhouse gas and air pollutant emissions, it's often seen as a worthy investment because there are very few transit buses compared to the number of cars. So in those first 2 scenarios of electrification, the exhaust emissions from the electric vehicles, so electric cars and electric buses, were removed, but the electricity production from nearby power plants was adapted to account for the additional electricity production needed for fueling the electric vehicles. And we've used here the current electricity grid mix of Ontario. And the third scenario is called the cleaner truck scenario. So here we've assumed that the trucks have recently been renewed and they're all younger than 8 years old. The rationale behind this choice is that there has been a dramatic improvement in air pollutant emissions of new trucks, but electric trucks are not yet a viable solution on a large scale. So here this graph shows the reductions in traffic-related greenhouse gas emissions achieved under each scenario. We see that deploying electric cars and SUVs will lead to the greatest reductions, with total GHG emissions about 2/3 lower than under the base case. And this is the case even when we consider the greenhouse gas emissions associated with the production of electricity, which is indicated here in green. Having electric buses or cleaner trucks will have little impact on the total traffic-related GHG emissions, which is because trucks and buses are not responsible for a large portion of the traffic-related GHG emissions. To put in perspective the results of the 3 scenarios, here I have compiled maps of the social benefits per 100,000 inhabitants. The color scheme is the same for the 3 maps. We see that the scenario with 100% electric cars and SUVs on the left and the scenario with cleaner trucks on the right would lead to similar health benefits. But it's electrifying the private household vehicle that is a lot more beneficial in terms of GHG emissions. Here, the calculations include wall-to-wheel emissions that are equivalent to fuel cycle and operating emissions. And the values provided assume that the electricity is produced according to the current grid mix in Ontario, but we've also simulated cases with different scenarios of electricity generation in Ontario. The region of Toronto is always benefiting the most from the strategies implemented, but we also see that under the cleaner truck scenario, the region of Peel would greatly benefit from improvements in air quality. So here we've seen that tackling emissions from cars and trucks would lead to the biggest improvements in air quality and the biggest decreases in greenhouse gas emissions. But it's also important to target transit buses because they drive in highly populated zones. So using these results, we can calculate the social benefits of deploying cleaner vehicles. Replacing one conventional car or SUV by an electric vehicle brings almost $10,000 of social benefit. And it's not only the electric vehicle owners that would benefit from an improvement from the electrification of the vehicle fleet, but it's everyone living in the GTHA. For trucks, replacing one truck older than 8 by a more recent truck brings more than $300,000 of social benefits. But why is it important to calculate the social benefits of alternative technologies? Because it puts in perspective subsidies provided for the acquisition of new and cleaner vehicles. So for instance, the current Canadian incentive for buying a private electric vehicles is $5,000, which is much lower than the social benefits brought by one electric vehicle. Ontario canceled a couple of years ago an incentive of $10,000, which we show here was in agreement with the social benefits of each electric vehicles. We've also modeled 2 scenarios of partial electrification of the cars and SUVs. So on the left, you have 20% electric vehicles, in the middle 50%, and on the right 100%. When we have low levels of electrification of the private vehicles, it's mainly the regions of Toronto and Peel that benefit from an improvement of air quality. The greenhouse gas emission savings are proportional to the level of electrification. And the key finding of this comparison is that under all these scenarios, replacing one car or SUV by an electric vehicle leads to about $10,000 of social benefits. This work was done in collaboration with the advocacy organization Environmental Defense, as well as Ontario Public Health Association, and the results were disseminated to the public, stakeholders, and political figures. There's a report on how electric vehicles and cleaner trucks can help reduce pollution, improve health, and save lives. That's available. And there's a website called clearingtheair.ca that has been created to provide information and to display the results. And so I encourage you to visit this website if you haven't yet. So now looking at a future that is a bit further along the way than electric vehicles and electric buses, what transportation policies will be important for us to consider in terms of impact on urban air quality? So in the future, ride-hailing and automated vehicles will affect driving patterns, speeds, vehicle consumption, and emissions, and they will have great impacts on air quality. It's essential to assess the impact of these new technologies on population exposure to design the most appropriate urban policies. And we also talk a lot about smart cities, and it's difficult to have a clear definition of what is a smart city. But ultimately, the implementation of new sensors in cities will impact emissions and behaviors and ultimately affect population exposure to air pollution. Also related to the future air quality is climate change. Climate changes will most likely bring increasing temperatures and changes in wind patterns. All this is going to have an important impact on air pollutant emissions. So for instance, there will be more wildfires and so more emissions of PM, and higher temperature will increase the emissions of VOCs from the vegetation. And as a result, PM concentration will increase, as well as ozone. And since Canada is affected by climate change through an increasing number of wildfires, for instance, it's important to anticipate the impact of climate change on urban air quality to be able to adapt our cities to the changing conditions. And so to do so, we will have to combine general circulation models, meteorological models, and air quality models. Moving on to the second part of my research, which focuses on urban design and air quality. So my research in this context is mainly driven by the question of how can we best design cities to minimize population exposure to air pollution. And here I'm also going to discuss two case studies. So first, I've been interested in looking at the exposure along the current and future bike facilities of the city of Toronto. I've also been interested in looking at the air quality in the areas for residential intensification, also in Toronto. Bikers are a category of the population that is vulnerable to air pollution because they exercise, and so they inhale more air than someone who is not physically active. And so it's important to install bike facilities in environments with the lowest possible levels of air pollution. In Toronto, there are 4 types of bike facilities. There are bike lanes, which are painted on the road, sometimes on the same name as cars. There are cycle tracks, which are physically separated from traffic. They're safer than bike lanes. There are multi-use pathways and laneways, which are often far from traffic and are shared with pedestrians. And there are trails, which are in parks very far from traffic. And so first I've looked at the exposure of cyclists to air pollution along the different bike facilities. So to respond to this question, in the summer of 2016, we conducted a large measurement campaign in Toronto. Here on this map, you can see the roads covered in black, which total 270 kilometers of routes, which were sampled many times over the summer by bike. And the pollutants measured were ultrafine particles and black carbon. After the measurement campaign conducted, I realized that the concentrations of ultrafine particles and black carbon on the bike facilities were not as expected. Here, this box plot shows the distribution of concentrations along the different facilities and along major roads and minor roads where there are no bike facilities, which means that the cyclists are biking among the cars. And what's interesting to notice here is that the highest concentrations of ultrafine particles and black carbon are experienced on cyclotracks, because those are built on very busy roads where space is allocated to them. But these are also the most frequented facilities because they're the safest and there is the most direct routes. And so this is concerning from a health standpoint. The City of Toronto has a 10-year cycling plan, which shows where bike facilities are planned to be built. And here they're represented in green. And after this first observations, I was interested in seeing the levels of air pollution on those planned bike facilities. But I had not conducted measurements along these future facilities, so I needed a method to estimate the concentration there. And so for this, I developed surfaces of air pollution using a method called land use regression modeling, LUR modeling. So LUR models are interpolation models that are based on measurements at various locations. Different variables related to the land use surrounding the measurement locations are considered as potential predictors of the levels of air pollution recorded. So these include land use, such as building footprint, residential area, but also the length of the roads, the bus stop locations, population density. And then LUR models are developed to explain the relationship between concentrations measured and surrounding land use characteristics. Those models are most commonly linear regression models, and they can then be applied and used to predict concentrations all over a city and develop what we call exposure surfaces, so maps of air pollutant concentrations. So based on the measurements conducted by bike, I developed exposure surfaces with average ultrafine particles and black carbon concentrations representative of the average summer levels in Toronto. So here I'm presenting the results for black carbon. The green color shows the lowest concentrations of black carbon and the red color the highest concentrations. So on the maps, the highways are displayed in gray and we see higher concentrations along them. We also see high concentrations downtown Toronto. And in general, we see that the road network is characterized by high concentrations. Coming back to the cycling plan of the City of Toronto, I intersected it with the surfaces developed before to estimate the concentrations along the future bike facilities. And then I compared the levels on the existing facilities with those on the planned facilities. So here this box plot shows the distribution of concentrations along the existing facilities in light gray on the right and along the planned facilities in darker gray. We've seen that we have significantly higher levels of black carbon on the future bike facilities, which is concerning because bikers are vulnerable to air pollution and they actually feel safe on bike facilities. So this simple study shows how important it should be to incorporate air quality in the design of bike facilities because it could impact the safety of bikers. It also shows how having an understanding of the current air quality at a high spatial resolution could help urban planners. Obviously, the cycling plan that I used back in 2016 has changed drastically over the last years and even over the last few months. But that doesn't mean that we should ignore the lessons learned here. Bike facilities have been installed along major axes such as Bloor Street, and traffic congestion there has not improved. If not, it actually has deteriorated, which means that cyclists biking along those bike facilities are exposed to high levels of air pollution. And another question related to urban design that I've explored concerned the land use policy of the City of Toronto and how it affects the exposure of the population of Toronto. So the City of Toronto has an official plan to guide the location of intensification and development through land use policy. It indicates the growth centers and the avenues targeted for intensified housing. Those growth centers and avenues are located along major traffic axes, here in pink, and mainly downtown Toronto in gray. Since air quality is usually poor along dense corridors, I wanted to see how is the air quality in the areas for residential intensification. And so using the map of air pollution of black carbon that I had developed before, I looked at the levels of black carbon in these different areas. So on the right, in light gray, you see the average exposure of the population of Toronto to black carbon. And in darker gray, we have the average concentrations in the growth centers and avenues. We see that on average, we have higher levels on avenues and growth centers, which means that the exposure of the population to black carbon will most certainly increase in the next few years. These are also crucial results that show how urban infrastructures should be designed to incorporate notions of air pollutant exposures. Sometimes setting buildings off by a few meters can be enough to decrease population exposure, or ensuring that public transit is accessible without setting buildings on busy roads. Obviously here, this is just an approximation of population exposure because the concentrations inside buildings differ from outdoor concentrations, but it gives a good idea of the outdoor levels to which inhabitants are ultimately exposed to at some point during their day. All of these were examples of studies that are important to date because they give us a good understanding of the current population exposure to air pollution, but there's still a lot to explore. So for instance, where should we build infrastructures to minimize population exposure? This includes infrastructures that house vulnerable populations, such as hospitals, retirement homes, schools, but it also includes outdoor infrastructures where people spend time or exercise, such as parks, bike facilities, athletic centers. Once we have identified the impact of climate change on air quality, how can we design cities that are adapted to the future air quality? How can we help people reduce their exposure to air pollution? How can we communicate information in a meaningful way? And finally, how can we design cities that are equitable from an environmental justice standpoint? How can we identify the communities that are the most exposed to air pollution? And how can we try to address this issue? To respond to this question, we need to have a good understanding of the current air quality. And to do so, there are different techniques that we could take advantage of. First, we could use new sensor technologies to conduct more measurements in cities. We could have sensors attached to bikes or cars, and which would provide real-time information. Or we could also set up sensors at strategic locations in the city. Could use novel data analytic techniques such as artificial neural networks to interpolate air pollutant measurements and predict air pollutant concentrations all over a city. Can use remote sensing techniques to extract more data on land use to get a better understanding of the relationship between land use and air quality. And finally, could develop citizen science platforms where data would be collected by the local population. This is actually a great opportunity to conduct measurements, but also to raise awareness and communicate on the issue of exposure to air pollution. So summarizing a bit, the research I've presented, the suggestions that arise from my research to minimize population exposure to air pollution include incentivizing cleaner vehicles on the roads, such as electric cars, electric buses, newer trucks. Include air pollution in our urban design of facilities such as bike lanes, areas for residential intensification. And conduct public outreach, because this is our best hope to raise awareness and get citizens to actively act for their health. To conclude on this, I think the overarching research objective of my work is to support the development of equitable and sustainable cities. Before moving on to the question, I'd like to acknowledge that the project I have worked on so far have been possible thanks to meaningful collaborations, and I'm very grateful for this. This concludes my presentation, and I would be happy to take questions.
Marianne, Laura, thank you for a fantastic presentation. That was great. That's a huge amount of information in a very short amount of time.
Yes.
Guessing that it may trigger quite a number of questions. While people are formulating their questions, I'll ask if you want to use the hand up option, which we can see, but also there's some questions on the chat. You can put them there. Azat has a question on the chat. Azat, do you want to ask your question, or I can read it?
Hi, Greg, how are you doing? Thank you, Laura, for the presentation. Can you guys hear me?
Yep.
Yes.
So it was with regards to the social benefits. You mentioned that one truck was almost 30 times the benefits of one car, but I'm assuming the number of cars we have on the road is more than 30 times the number of trucks. So if we had to prioritize one over the other, which one would you pick?
This is a good question. I think there's no clear answer to this. It's obviously we need to focus on both. Prioritizing cars, I think it's important to have cleaner vehicles on the roads, but it's also important to have less cars on the roads as well. And it's the same for the trucks. So there's been a lot more truck traffic in cities in the past years because of online shopping and associated deliveries. And so I can't really give you a clear answer on this. I think it's important to tackle both. Ultimately, trucks are driving in many different regions, provinces, and so they have an impact that is even further away than just within the GTHA. So tackling emissions from cars would impact a much bigger population than just looking at cars.
Thank you. There's a question from Phil Blagden. Phil, do you want me to read the question, or can you use your microphone?
Oh, I can speak to it. So I was just curious, and I might have missed it, when you did the social benefit calculations, were you just looking at the air pollution benefits? Because you had the greenhouse gas reductions as well, did you calculate a social cost of carbon into that value?
No, so the results I presented here don't include the social cost of carbon. And so ultimately the social benefits, if we were to include benefits associated with reductions in greenhouse gas emissions, would be bigger.
Yeah. Another question, did you also look at in terms of miles driven? It looked like you were looking at per vehicle, per truck, per bus, and I guess it was just like number of people transported over a different distance. It's hard to do with the transportation of goods, but it might be useful as well.
Yeah, we could do it by number of cars, but not by number of kilometers traveled, because the output we got from the traffic assignment model, especially for trucks, it wasn't accurate enough in terms of number of miles traveled.
Okay, yeah, and I'm showing my age by saying miles instead of kilometers. Thank you.
So if people want to ask a question and you're not familiar with Teams, on the top there is a hands up, or beside that there is a chat, and you can put your questions in there as well. Let's see, I don't see any questions yet, so I'm going to ask one. Just want to make sure I don't, because I've had lots of chances to ask questions, but I actually have a new one. So you mentioned the urban intensification and the idea as well that the bike paths are going along roads and there is increased congestion, so that you showed some black carbon data that the cyclists, even though we're putting in more cycle paths, we're still getting more exposure. So we haven't managed to get over the peak, or so to speak, to the point where it's actually causing us a net reduction overall. I'm wondering, have you looked at the idea of low emission zones? So this week there was a report from London, England, trumpeting how much success they've had in the last 4 years in dropping concentrations of NOx and black carbon by putting a low emission zone. And I'm wondering if you could combine your two studies and show if we were just to take some of the heavy emitting vehicles, for example, the trucks, off the cycle routes.
Yes.
Would that eliminate the black carbon so we don't actually have to solve the whole congestion problem in order to help the cyclists? We just need to get rid of the high offenders. And so that's a lot. So you can deal with that any way you want to, but what do you think?
Sure. It's a good point. Yeah, definitely removing trucks from roads where cyclists are biking would be very beneficial in terms of local air quality. The question is always of where are those trucks rerouted? So that's the issue with low emission zones. You remove traffic from a specific zone, but you don't necessarily tackle the issue of congestion and and reducing traffic. And so you might reduce traffic in a zone, but have a lot more traffic in a parallel street, for instance. And it's hard to know if there are actually benefits in this, depending on where the traffic goes. We've seen it with King Street. There's a lot less traffic on King Street, obviously, but it's been rerouted to all the streets around. And ultimately, we've been seeing very little changes in air quality within the neighborhood because there's still substantial traffic there.
Yeah, and I think that's where some of Matt Rauda's work on off-hour deliveries, because certainly we need to get the freight in to where the people are, and the people will be where the dense urban living is. But we don't necessarily need to do it when they're at the time when the cyclists are busy going about their daily lives. So there's probably a balance, so it might be possible. Other questions? Just jump in if I've missed you with a hands up or on the chat. Taylor, I see you've got a question.
Hi, yeah, actually, I was curious about the model framework that you showed us in the beginning and how adjusting the inputs to that model might change the outputs if there were any, like if you did any sort of sensitivity testing and if there were any surprises in that. For example, if we found out a year from now that trucks are emitting twice as much as we already thought they were, would that significantly change your results? Or if the model is far too complex to handle that sort of fine tuning like that?
No, it would actually pick up on changes of emissions. We've run some scenarios with trucks actually looking at the influence of truck traffic on the highway 401. And one scenario that I ran was looking at what would happen in the air quality in the region if we were to decrease by half the emissions from trucks only on the highway 401. And we've seen dramatic improvement in air quality around the highway 401, but even within the city, the GTHA, resulting from such changes in emissions. So this model, because it is at a fine spatial resolution of 1 by 1 kilometer, we can really see impacts of important emission sources such as traffic.
There's a question here, but unfortunately the user's name is not given, so he's as an unknown user, about the separation of how much air quality would be improved if we installed separate bike lanes, which I believe are the bike, I can't remember what you called them, but the separate bike lanes. Would it improve the air quality? And I believe in some places they've actually looked at putting in partitions, so barriers that don't just go up to a foot or two, but actually go up to the height of the cyclist. What do you think about that? Do you think that would improve the air quality if we actually put high physical barriers, and would that be a good idea?
My name's actually Christy Cole. Sorry if I don't know why
Sorry,
my
Christy.
name isn't appearing in the in the chat, but anyway, I mean, I wasn't really thinking so much about the barriers, but I know that, for example, the installation of a separated bike lane on a busier street can sometimes reduce the speed of traffic, can sometimes reduce the traffic, the car traffic in the neighborhood. And so I was just curious to know if the model actually demonstrates if there was a quantitative value that was perhaps associated with this change.
So the work I've done on bike facilities is based on empirical data. So I couldn't really run any scenarios. And of course, when you're going to install a bike facility on a specific road, you're going to alter traffic patterns. And the issue with the large modeling framework that I have showed before is that the spatial resolution, even if it's fine at 1 by 1 kilometer, it's too big to look at the impact of changes of specific bike facilities, because these are going to have a very local impact on air quality, well, on traffic, and so on air quality.
Okay, yeah, I just wondered if, because while it's still a 1 by 1, I mean, it does impact not only the cyclists, but even probably the pedestrians who were walking on an adjacent sidewalk. And so I was just hoping for as much detail as I could get on that question, but thank you.
Sure, but these are good ideas of scenarios to run, but these would also, this type of scenario also meant that people's behavior is going to change, so they might change their mode of transportation when you install bike facilities at specific locations. And so these are the type of scenarios that I haven't run, but we're looking at running in the next months, looking at changes in behaviors and see how it's going to impact traffic patterns, traffic emissions, and ultimately air quality.
Thank you.
Are there other questions? Here we go. Go ahead. I can't see who it is. Abuzar, I think your question, can we generalize the obtained results for black carbon effects on cyclists to other pollutants like NO2?
I would say yes, because NO2 is also a traffic-related air pollutant. So we've seen a lot of correlations between NO2, black carbon. Black carbon is really associated with diesel emissions. So it's not going to be exactly the same impacts, but there are going to be similar patterns for sure.
Any other questions? I've got one. It's a rather leading question, so you can choose not to answer it. So your work has shown that the social benefit for replacing one of the older trucks is over $300,000, which is more than the cost of buying a new truck. Can you think of any reason why the government shouldn't put an incentive in place to incentivize at least part, if not fully funded, replacement of these old trucks?
Why the government shouldn't?
Yes, why it shouldn't. I can think of lots why it should, but can you argue why it shouldn't?
Oh, well, I think because we need ultimately less trucks on the roads, and finding solutions less polluting, or like even reducing our dependence on trucks would for sure be a lot more beneficial on the long term.
We've got 2 more questions here and then we'll cut it off. James, do you want to ask your question?
Sure. Can you hear me, Laura?
Yes.
Yeah, so I summarized it in the chat, but yeah, it was really a great presentation. I was really happy to see that you addressed some of the intensification questions. I was curious, like, if you'd ever seen this or if you had interest in like with projected intensification, like you probably saw how like in Toronto, it's all supposed to be happening along mostly busy corridors and like these mixed use areas. So I was interested in the idea of like the benefits or trade-offs, like if you were to like dilute that intensification and incorporate residential neighborhoods, like, because I mean, as a question for planners, like even to show the benefit of like a 10% increase or like 10% movement of that population into a residential area could show a meaningful population reduction in pollution exposure, but I was curious about your thoughts on that.
Yes, for sure. Moving the population to residential zones that are in between major roads would be a lot more beneficial in terms of exposure. The issue is that it would require an intensification of housing within the residential areas, and there's been, well, the population in Toronto has been very reluctant to doing that. So I think that's part of a reason why intensification housing is along major traffic axes, is because there's a lot of there's not consent from the rest of the population to put higher buildings within more residential zones.
Yeah, I think I agree. It seems like it's very politically unpopular.
Yeah.
And the last question comes from Priya. Priya, would you like to ask your question?
Sure, yeah. I was just curious if you compared the results of your chemical transport model in terms of the actual air pollutants to any like ground source monitoring campaign and how they compare to one another.
Yes, so the model has been validated with stationary monitoring within the DTHA, and so we've been quite good at. There's been mainly comparisons with NO2, ozone, and PM2.5 because those are the pollutants that are measured. We've had a bit more troubles validating the ozone because we tend to simulate higher levels of ozone than what has been measured at those stations. But I think this is a problem that is common to chemical transport models in general.
Okay. And that, I want to thank everyone for joining us today. In particular, I want to thank Laura for a fantastic presentation. It's always interesting to hear your work. And encourage everyone to join us at the beginning of November when Jenna is going to talk about her work, and we'll send out some publicity about that in advance. So thank you again, and the recording for this will be available on the SOCAAR site probably in the next few weeks. So thank you all for joining us, and big round of applause that Laura can't hear, but it's happening right now.
All right, thank you, Greg. Thank you for inviting me.
Yes. Oh, we're getting lots of thank yous to you.
Oh.
There we go. Yeah, I thought you did a wonderful job. So it's